We're going to continue our work on integrals. This isn't necessarily a new integral technique, but it is a new way to look at integrals. So we'll just dive right in and start talking about these improper integrals. So remember, in the definition of the definite integral, we assumed that the limits of integration from a up to b would be finite. In other words, we assumed that this was telling us to accumulate the area in the plane trapped in between our function and its horizontal axis, and we would get some real number value as a result of that, because we had a bounded area. Every definite integral we've worked with up to this point, we've had a bounded area. There was a starting place and a stopping place, and there was a definite area that we could use the fundamental theorem and find the exact area of that. So there are applications in mathematics where it's helpful to allow one of your limits of integration, a or b, or sometimes even both, to be infinite. Here we have an upper limit where we're accumulating the area in the plane trapped between our function f of x and its horizontal axis, starting at a, but going all the way down as n tends toward infinity, positive infinity, on the right end of the x-axis. So ideas come into play here about, number one, what does that area represent? Is it a bounded area? And does the area actually have a real number value? And we could do the same thing with our lower limit. We could do the same thing with the entire horizontal real number line. This is still telling us to accumulate the area in the plane, starting at the left endpoint and stopping at the right endpoint. And these integrals are called improper integrals because it's not proper to actually plug infinity into any sort of mathematical work. We've always found the antiderivative function before and evaluated it at the upper limit minus the lower limit. And I've taught you all year long that you just can't pick up infinity and plug it in like it was a number. We've talked about the idea of huge and tiny and all those things when we were talking about limits. So that's what makes this improper. It's not a bounded area. We can't guarantee that it is bounded if we're going to infinity or coming from infinity. And there are two types of improper integrals. One that has infinite limits, our limits of integration, and then the second type, which we'll see in another set of videos, will have infinite interior points. So let's talk about what this is going to look like. All right, so let's say I have the definite integral from negative infinity up to b of f of x dx. As I stated a while ago on the last slide, we can't just plug infinity in and go to town on the fundamental theorem like we always have with our real numbers. Now we're going to have to introduce the idea that we're tending toward infinity, either negative infinity or positive infinity. So the limit has to come into play here because we're never, remember, we're never at infinity. The best we can hope to be is near. We can only be near infinity. There's no way in the world for us to actually arrive there. It's large without bound. And without bound means we never get there. We can only just get an idea of what's happening as we get very, 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 very close. So you can see here, notation is going to play a big role. So I'm going to be watching your notation very, very carefully. It doesn't matter what letters that you use there. We are used to the lower limit being a, we're used to the upper limit being b, so you'll see this a lot. The limit as a approaches in negative infinity, or the limit as b approaches positive infinity, but those aren't hard and fast rules. They're just generally what's used by mathematicians. Now, Another big idea that comes with these improper integrals is an idea of what the result means. What's actually happening out here, because we are still accumulating area in the plane, just like we've always done with our definite integrals. But what does that mean? How can we use the idea of the result from these improper integrals? So we find that if these limits to the right of the equal sign here, if they exist and have a finite value, we can actually do fundamental theorem inside that limit and we get a real number value, then we say that that area in the plane, that the area, unbounded area, that's represented by this improper integral, if we get a real number finite value, we say that that area converges. Okay? So the corresponding improper integrals converge, and they converge to those values that we find doing good calculus. Otherwise, the integrals are said to diverge. So basically what we're doing is we're going to see if we get a real number value from our work here. And if we get a real number value, then we can say that this integral converges. In the absence, and this needs to go in your notes, in the absence of convergence, we have divergence. And divergence can look like several different things. Divergence doesn't have to look like just, a whole lot of area or an amount of area that's tending toward infinity. That's one definition for divergence. But also divergence can be an area that never settles down. So there's two different types. Those are the two main types. Here's the graph of a function. And let's say we were trying to see what the accumulated area from negative infinity to positive infinity was doing for this function. Well, graphically, it looks like from negative infinity, and as we go toward positive infinity, it looks like it's going to be a finite real number value. There's just not a lot of wiggle room between that x-axis and the function. And it's highly likely, although not 100%, it's highly likely that that would converge, because the function hovers right above that x-axis from negative infinity all the way up to positive infinity. And that's the idea of convergence, is the idea that even though this is an unbounded interval, that over time, and infinity has a lot of time, and over distance, that we might say that that area converges to the value that we find from this integral. But what if we have a function that from negative infinity to positive infinity hops above and below for the same amount of area, above and below that x-axis? Remember, here's a positive amount of area, here's a negative amount of area, and it's the same. So those areas, when we accumulate, undo each other. So right here, I start with 0 area. Right here, as I accumulate from left to right, I have positive area. And right here, I'm back to 0 area. And then right here, I have the same amount of positive area. And then back here, I'm back to 0 area because there was the same amount of negative area. That's what it looks like when we say that the definite integral or improper integral diverges, where the area never settles down to one value. All right, so I know this is different. I know this is a different way to look at the result from a definite integral. And I know that students are uncomfortable right off the bat with this idea of convergence and divergence. But the more we work with it, the more comfortable that you will get with it. It's not difficult, it's just different. And these improper integrals, both types, give us a really good footing, a really good basis to start our series work, because convergence and divergence have a lot to do with our series. So you'll get more and more comfortable with it. Don't worry about it. I know it's kind of a new concept. All right, so let's just do an example. Does the area in the plane converge or diverge for this improper integral from 1 up to positive infinity between the function e to the negative x and the horizontal axis? Well, this is just a matter of evaluating this improper integral. And we're going to have to do that inside of a limit. It's the only way we're going to be able to talk about the area that's trapped in an unbounded interval. So I introduced the limit. I'm going to put my integral inside of a limit, and we're going to see what's going to happen to this area as the upper limit tends toward infinity. So we're going to do what we've always done before. We know how to evaluate definite integrals. That hasn't changed. We can still use u substitution. Now I'm going to come outside of the definite integral, and I use the indefinite integral. Remember? So I don't have to worry about converting to u values for this. And so the antiderivative function here, the meat of it that I'm after, is negative e to the u. So I'm going to come back and pop that into my definite integral, and the result is negative e to the negative x. And I'm showing the AP reader that I'm going to do fundamental theorem. So what we know already about evaluating integrals is unchanged. There's just a little change in notation. So I have the limit as b approaches infinity of negative e to the negative b. There's my upper limit in my antiderivative, minus e to the negative 1. There's my lower limit. Now notice the whole thing is inside the limit. And that's okay, because the limit of a constant is a constant. So that's not going to be an issue for us. We're still going to be able to evaluate this limit. Now, when e is raised to a negative exponent, especially inside this limit idea, I think that I would put it in the denominator with a positive exponent. I think it's going to make this easier to evaluate. So this becomes negative 1 over e to the positive b minus negative positive 1 over e, or e to the 1, which we would just say was e. So now I'm ready to evaluate my limit. Remember, this is the idea, now that I'm actually plugging in, this is the idea where we can't just write e to the positive infinity. This is the idea where we go back to huge and tiny. Okay? So if I have a real number value, and I do here, which is negative 1, and I divide it by a huge number, and I am dividing it by a huge number, then this term goes to 0 inside that limit. So the area trapped in the plane underneath the function e to the negative x, starting at x equal 1 and going to positive infinity, if we start here at x equal 1, this area converges. And it converges, according to my improper integral, to a value of 1 over e. So it converges. All right, we'll stop here. I have some more examples to do, so look for the next video.